Bayesian analysis. Then we'll be going into MLE, MAP, prior posterior framework, all these things. Slowly, we'll be unfolding all these things. Now, yeah. So here basically the real mathematical underpinning will be starting. Okay. So acha. So before starting, can I just have a survey kind of that how many of you have taken course in your UG, PG, or Saurav Ranjan sir has already raised his hand. So sir, please ask, listen the question first, sir. Yeah. So how many of you have actually taken some statistics course? I think many of you are now into this predictive analytics, machine learning, AI. But how many of you have taken a formal statistics course in your UG or PG? Okay, I can see around 6-7 hands have been raised. Okay, acha. Now how many of you? Okay, so 2 more. Okay, acha. So how many of you have gone through something called as Bayesian statistics? If you are having any kind of idea about Bayesian statistics and all these things, sort of. Okay, Suman, Deepak. Okay, Antariksh. No, the word has hand. Okay, only 2. So at what level you have done this Bayesian statistics? Can you just speak up if you can tell? At what level?
So, sir, this is Saurav here. So,
Yes.
sir, actually, I'm a PhD scholar from IIT Kharagpur. So, what
Okay,
I
very
do is
good.
I use choice modeling. I'm from
Okay.
BSOM actually.
Okay, okay,
So,
choice modeling. Yes.
So I use choice modeling. Here in the
so,
choice modeling, is
yeah, please
Bayesian
go.
update.
Okay, okay. So, acha. So you are doing this choice based on negative binomial distribution or anything? What kind of likelihood you are using and all these things? Because we are. Yeah.
It's a binomial distribution only. It's
Binomial distribution
pure
only.
binomial distribution because
Achha.
because of the y variable being 0 and 1, so it's purely a binomial distribution. But we are updating the likelihood function as it keeps on, the data keeps on gets adding and adding.
Okay, and another thing is that what kind of simulation methodology you are using? Simulation methodology, I'm asking in terms of this Bayesian simulation, not about the coding or anything. Okay, so what kind of simulation methodology you are using?
So
sampling based
mostly,
or?
sir, so yeah, so it's a frequentist only, but sir, the thing is, over there we're using Monte Carlo Markov chain types of
Markov chain Monte Carlo, MCMC. Okay.
MCMC,
Okay.
yes.
Okay. Thank you. Saurabh sir, Dr. Saurabh Ranjan. Can you please speak up a little bit? You have raised your hand. Okay. Acha, Mr. Prabhu. Mr. Prabhu, you want to say anything? Okay. Acha, so basically, I'll be starting with this particular Bayesian simulation, Bayesian analysis, not simulation. Simulation will be a little bit later. It will be coming because in the afternoon, the step-by-step methodology will be developed to solve this kind of parameter estimation problem in any kind of predictive analytics. So till now, it was on a very rudimentary level, and almost everybody, they have done some kind of this kind of analysis that in a frequentist way and some kind of Bayesian way, like this in a particular bag, suppose some few colored balls are there, means mixed colored balls are there. Then if I am basically selecting a particular bag randomly, and then I am picking out one ball out of that, and what is the probability that it is of a particular color? Okay, this kind of thing. So in these situations, basically we are going for this kind of Bayesian Bayes theory. Okay, Bayes theorem or Bayes theory, and in which we are actually using at the core of that Bayes theory, that is basically conditional probability and joint probability. So I'll be starting step by step, and I'll be very happy if you start taking notes, because I'll be using pen and paper kind of explanation. I'll be doing. So in slides, basically I'll be writing everything. So the topics I'm going to cover Okay, so here in this particular session, the topics I'm going to cover, just let me show you. Sorry. So can you see my slides? Can everybody see my slides? So
Yes, sir.
yeah, okay. Okay, so basically in this I'm going deeper into this Bayesian analysis. So little bit idea you have got that what kind of analysis we are going to do in this particular program. So Bayes theorem will be at the core of this particular probabilistic MLTL. Okay, so what are the topics we are going to cover? So first is I'm going to look at this concept of random variables once again, then the probability mass function, probability density function, cumulative distribution function, expectation and variance calculations, moments calculation. Okay, so moments are basically nothing but they are in the generic form of this expectation and variance. Means you can actually club them in a particular using a particular term that is called as moments, and these are nothing but the distribution the properties of the random variables. Okay, these are the basically properties of the random variables, right? Acha. Then some popular PDFs we are going to look at. Okay, so among that those PDFs I'll be sharing full acha, how many of you know of a particular book that is basically authored by Christopher M. Bishop? Okay, pattern recognition and machine learning, that is freely available over net. Okay, internet. I'll be mostly following their notations, and that's a very nice book to start with. Beginners, it is very nice book to start with. So you can actually have a try. Okay, I'll be sending you a little bit, you can say pages of that particular book to go through, so that you can be you'll be updating yourselves. Okay, for these particular things. Okay, I'm not telling you that you have to remember everything. Okay, because this Bernoulli distribution, binomial distribution, beta distribution, multinomial, they are really yeah, name of the book is Pattern Recognition and Machine Learning by Christopher M. Bishop. Okay, so let me write it in the chat box. Just 1 minute. Chat box. Where is the chat? So pattern recognition and machine learning by Bishop. Okay, so you search it, you'll be getting the PDF over internet. Okay, and if you are not able to find out, okay, I'll be later I'll be sharing it with you, and that is freely available. Okay, no need to worry about this. Yeah, Christopher M. Bishop, pattern recognition and machine learning. Okay, there is another book which is in little bit more detailed way. Okay, so that is by Kevin P. Murphy. Okay, but it is a little bit more detailed way. Okay, so better is you start with this particular Christopher M. Bishop. Okay, so the other one is machine learning probabilistic perspective by Kevin P. Murphy. Okay, so this is another book. Okay, so right now there are two parts of this particular book. One is the introductory machine learning a probabilistic perspective. Another is the advanced models. Okay, so you can actually these are also available over net. The draft versions are available, but you can use it. You can use it, very nicely written. But this is in a more depth than Christopher M. Bishop. Christopher M. Bishop, he has actually touched many things. He has not gone to the depth of that. Okay, but to strike the ideas and all this, ignite this particular this kind of you can say the intuitions and all these things for this probabilistic machine learning, deep learning, that is very well covered. Okay, so these are the two books I'll be following. Okay, and I'll be giving the notes also, so you don't worry about that. So we will try slow. Acha. Next is that we'll be talking about something called as a distance function that will be known as scale divergence. Okay, this is pullback labeler divergence measure. Okay, then we'll be going into this Gaussian distribution, and Gaussian distribution will be trying to cover it as much as possible. That in case of univariate, in case of multivariate, how it is actually working, how does it look like? all these things. Then we'll be going to something called as transformation of distributions. Then we'll be going to rules of probability, which was already covered in the earlier session. But I think as many times as you can basically be in touch with this particular formula, rules, and all these things, I think that will be creating that will strengthen your foundations. Okay, so that's why I'll be covering it once again, that law of total probability product rule. Then we'll be going into Bayes law. Okay, Bayes law means that has been already covered, but I'll be covering it once again in the prior posterior framework. And then we'll be going into this particular maximum likelihood estimation, that is MLE, and then maximum a posteriori estimation, that is MAP. Okay, so this is the basically scheme of this particular session. Acha, now just setting the stage, let me just briefly actually cover many little bit, you can say, introductory things which you already know, but let me just cover it once again so that you can actually, it will be kind of recapitulation to it. Okay, so first is that we are in predictive analytics. Okay, so can you see my writing?
Yes, sir.
Okay, so this predictive analytics is basically coming as the second one in the you can say the in the paradigm of analytics. Okay, in the paradigm of analytics. Okay, so what is the first one? First one is called as descriptive, where we are interested in describing the situation. Second one is called as predictive analytics. We are actually trying to predict something based on the description of the data. And the third one is actually prescriptive analytics. Prescriptive analytics. So in prescriptive analytics, so how many of you know about prescriptive analytics or come across this particular term? So can you raise your hands? So okay, anybody else? So these are the basically three paradigms of analytics. Okay, so this is for prediction, this is for description. So please remember the number. Okay, and this is the prescription. Okay, that means how this prescription is actually different from prediction and description. Prescription means that suppose you are the consultant, okay, and your client is asking for what should I do? Okay, I'm having this data, you have predicted something, but tell me concretely what should I do so that I'll be able to generate more revenue. Suppose if I tell you, if he is asking, the client is asking, then basically you have to go into this prescriptive analytics, where it is a kind of decision making framework, and mainly these operations research models, optimization, okay, many things, all these things will be coming into this particular prescriptive analytics. So this is basically, these three are the paradigms of analytics, first of all. Next is that just a brief recapitulation that measures or you can say prescriptive analysis is a data analysis that recommends best course of action. Yes, for a given situation by analyzing data considering various factors. Yes, very good, very good. So let me just I think you already know this thing, but let me just write it so that it will be easy reference. That scales of measurement. So how many scales of measurement are there? That is basically 4 scales are there. Okay, first is known as nominal. Second is known as ordinal. Third one is known as interval. And fourth one is known as ratio. So why I'm calling it out? Because we'll be dealing we'll be dealing the cases of discrete variable and continuous variable. Okay, so this nominal and ordinal, they are coming into discrete one. Okay, discrete one. Now how they are different, nominal and ordinal? Nominal is basically they don't have any kind of ranking of the values. Okay, so they don't have any kind of ranking of the values, whereas this ordinal is actually having the ranking of values. Okay, so this is how actually they are different, right? Now this interval and ratio, they are known as continuous scale. Okay, they are known as continuous scale. Now interval and ratio, you can actually find it out. I'm not going into detailing to all these things, but these are actually categorized under continuous scale of measurement. And in among interval and ratio, ratio data are more prevalent. Okay, ratio data are more prevalent, and that is basically coming under this particular continuous scales of measurement. Okay, now why these are actually important? Because we have to talk about something called as random variables. Okay, so random variables. What are random variables and how they are actually different from simple variables? Simple variables don't have any kind of chance or probability associated with its values. Okay, with its values, right? So if I tell you that a person's height is suppose 5 feet 9 inch. Okay, right? Now the thing is that after measurement I have found it out. Now if I tell you that uh, there is 60% probability that the person's height is uh, 5 feet 9 inch. Okay, then whenever this kind of probability is coming into picture, chance is coming into picture, then this height now no more is a simple variable. It is now a random variable. Random variable means that whenever I am having a particular variable taking a particular value, having a chance associated with it, okay, so then it will be called as a random variable. So random variable is basically variables whose values are dependent on chance of occurrence. So probability is actually associated with this particular value, okay, with of this particular random variable. Okay, so this is how basically we decide. Okay, uh, mm, next is this thing. Okay, sorry. Now next side is basically how many of you are actually conversant with these two terms, that parameters and variables. Okay, so in any case you'll be dealing with this particular two terms. Okay, and many a time basically we are getting confused with these parameters and variables. Okay, now parameters and variables, basically if I want to discuss, then I'll be telling that if a data generating process, okay, how the data getting generated. So data is getting generated. Suppose if I tell you about this suppose any kind of random experiment. Okay, any kind of random experiment. Suppose I am having this particular coin tossing, let's say. Okay, so coin tossing, I am tossing a particular coin, and I am interested in finding out that what is the proportion of head and what is the proportion of tail. Okay, now the thing is that first I can actually fix it. Okay, so that will be basically equally chance outcomes. Okay, equal chance outcomes kind of experiments, that I am basically telling that as they are having two possibilities, head and tail, so let us take it as 50-50. Okay, so this is the first of its kind. Next is that I can actually uh, have number of tosses. Okay, suppose 50 tosses I have done, and out of 50 tosses, suppose 28 times this particular 28 times this head has come, tail has come, and suppose rest of the times 20 times this particular tail has come. Okay, so now what I'm doing actually, I am basically taking the frequency, okay, frequency of the event. Okay, and then I'm trying to find out that what is the proportion of head and what is the proportion of tail. Now this is the second category, and third category is basically that I am having some kind of prior information with me. Okay, I am basically telling that they are equally probable, and then I am trying to do tossing, and based on that basically I am updating my belief. So the third kind of is basically called as Bayesian methodology. Okay, so first one is equally probable, second one is frequency based, third one is basically Bayesian methodology. Now the thing is that what actually we are doing here, we are actually trying to find out that what is the probability of head and what is the probability of tail. Now what is this actually? So this is basically the parameter of the data generating process. Okay, this is called as the parameter of the data generating process, right? So parameters, basically what happens that if you are in frequentist school of thought, okay, frequentist school of thought, then parameters are taken as constant and data is taken as variable, right? Now if you come into this Bayesian methodology, okay, so Bayesian, if you come at, okay, then basically what happens, these parameters are taken as you can say changing. Okay, so this is a kind of variable here, and the data, they are taken as constant. And as you are actually doing step-by-step experiment, this more data will be coming. So for one iteration, these parameters are known as variables. Parameters are always variables in case of Bayesian, and data is actually taken as constant for a particular iteration. So this is basically the two schools of thought they are thinking about these parameters and variables. So parameters are basically those entities you want to estimate. So parameters are the estimates, okay, uh, parameters are the entities which you are going to estimate. Okay, so parameters are the entities that are to be estimated, right? So and whole this predictive analytics actually, or you can say the this all this machine learning and all these things, basically they are trying to find out, everybody is having this particular objective. Okay, now with this objective we can have actually different paths by which we can reach to that goal. Okay, but the goal is actually the same, that you have to estimate the parameters, right? Achha, next is that this is the one. Achha, now many of you have so let me just test your understanding regarding this. So many of you know about linear regression already. Linear regression. Okay, because why I am talking about this particular linear regression? Because every time you'll be finding out that in some way I can actually connect it with the linear regression, okay, or regression methodology. So regression is basically there will be a set of predictors, okay, set of predictors, okay, and I'll be having a response variable. Okay, so this response is actually a function of these predictors, right? And there will be some kind of unestimated, or you can say, or unmodeled component, which will be known as error term. Okay, and all the randomization is actually revolving around this particular error. Okay, all these randomization and all these things will be revolving around this particular error term. Now the thing is that linear regression is actually coming under something called as supervised learning framework. I think everybody know a little bit about supervised learning. What is this supervised learning? Supervised learning is basically that you are having a response versus predictor set data with you, and this given response, okay, the response given, that is actually is working as the supervised supervision. Yeah, having gone through various models like binary linear regression, why it is so important to go for Bayesian method. Yeah, I'm coming to that. I'm coming to that actually. So supervised learning, right? Supervised learning, basically it is telling me that I'm having a response versus predictor data set with me. So all basically here are, in most of the cases generally, will be having some kind of tabulated data. Okay, so this is suppose a response here, and this is suppose predictor 1, predictor 2. Okay, so here generally response we denote by y. Okay, so this is suppose y1, this is suppose x1, this is suppose x11, x12. Okay, that means first row, first predictor value, and first observation. So this is basically the first observation. Okay, so response versus predictors. So this is first predictor, this is second predictor, like this it will be going. Okay, so in this way generally we have our data with us, and based on that basically we will be finding out. Okay, so this is in case of supervised learning. So, and in most of the cases basically we'll be trying to if tabulated data is available, that is very good, and if tabulated data is not available, then we have to make a structure like this. Like there is something called as unstructured data. Okay, so if you talk about text data, then that is basically unstructured data, and from that unstructured data you have to create this kind of structure. Okay, you have to create this kind of structure, then actually it will be very easier for us to deal. Now supervised learning is telling you that there is somebody who is supervising you, okay, to learn the data. Okay, to learn the data, somebody is actually supervising you. Okay, so this is basically supervised learning. But there is another kind of learning framework that is known as unsupervised learning. Okay, so unsupervised learning is basically no supervisor with you, no supervisor, nobody is supervising. So where it is applicable, that suppose I want to find out that if I'm telling you that many of you are actually subscribing to news apps. Okay, subscribing to news apps. Suppose every day around 5,000 10,000 articles are being written by many news agencies. Okay, and they are basically coming to your this thing, coming to as a suggestion to you. Okay, based upon your search and reading habit. Okay, now the thing is that how do they do it? Okay, they are basically trying to find out that they are trying to group the news articles. Okay, they are trying to group the news articles into some number of groups. Okay, and based on that they are actually matching with your reading habit and searching habit. Okay, and based on this they are actually recommending this to you. Okay, so this is actually coming under a recommendation system. But I have done it, I have basically told it in a very crude way. There are many things inside, but I'm not going into that. Okay, right now. Achha, the third one, there is another kind of learning framework that is known as reinforcement learning. Now, what is this reinforcement learning? In reinforcement learning, basically, we are actually working in a, we are working by our own, okay, by setting some kind of reward penalty scale. So suppose if we are successful, then we are actually patting our back. Okay, very good, very good. So give us some kind of reward. And if we are doing anything wrong, then some kind of penalty will be imposed, so that, yeah, learning from our mistakes basically. And I can give you a very lucid kind of example. And I think everybody, you can actually will be able to correlate it. That suppose whenever you are learning, suppose riding bicycle or bikes. Okay, so are you basically learning it in terms of that, okay, if I press the pedal in this much with this much dyne of force and this angle, then only I'll be moving to this particular angle. Okay, so we are not going into that detailing. What we are doing, that if starting riding the cycle and if we are actually falling, okay, then we should not do that kind of mistake. So we are actually learning from our mistake. And if we can ride it straightly, then basically some kind of reward you are giving to yourself. So continue this. Okay, so in this way, so this is basically you are reinforcing your learning. Okay, so there is no supervisor, you are not having any kind of supervisor with you, nobody is helping you. So now you are giving this reward or penalty, okay, based upon your actions. Okay, so these are basically three learning frameworks. Learning frameworks. Now we are coming to that this learning. Okay, suppose supervised learning, unsupervised learning, reinforcement learning, whatever it is. Okay, so everywhere, what is your main objective? Main objective is to estimate the parameters. Okay, now whenever you are trying to estimate the parameters, the first question comes into mind. Okay, first question coming into my mind, that how much data I'm having. Okay, so how much data points I'm having. Because it is always known that larger data, okay, will be giving you better estimates. Okay, it's always there. Now the thing is, that question is that suppose you don't have that much data with you. Okay, it's a kind of small set of observations, right? So then what you do? Sometimes what happens that you are having the tabulated data with you, and it is not filled up properly. Okay, it is not filled up properly. Okay, so this is called as sparse data, or filled up properly or not filled at all. Okay, many where you the responder is not actually replying. A responder is not telling about the you can say about a particular variable, that okay, this is the value of that particular variable for my case. Okay, they are not telling, they are not revealing. What will you do? Okay, so data points, if you have a large data points, okay, large size of data, that will give you, then you can actually safely go for frequentist kind of approach. Frequentist kind of approach. But if you are not having that large size of data, okay, that is small data, the data size is small, okay, sparse data means that in that data set many entries are actually missing. Okay, many entries actually are missing. So in that case you can go for Bayesian approach. Why? Because the frequentist approach might fail in those cases. Okay, now there are some more advantage of Bayesian approach is that in frequentist approach you can actually have only point estimates, okay, and interval estimates. Interval estimates are actually derived from point estimates. Okay, naturally you cannot get that. But in Bayesian approach, what happens that you can find out the distribution, okay, or probability distribution of the parameter, okay, all total. Okay, distribution of the parameter. Now, what is the usage of this particular distribution of the parameter? You can actually have any kind of statistics from that. Okay, so it helps in not only finding out point estimate, not only find out interval estimate. So are you aware of these particular point estimates, interval estimates, and all these things? So if anybody is not aware, please raise your hand. Point estimate, interval estimate, then several other statistics, Jiva. Okay, so you have not gone through this point estimate, interval estimate anywhere. Okay, so let me just give you a small example, then I will tell you. Yes, I'm telling you. So several other statistics of the parameters. Acha, what is the difference between parameter and statistics? Can anybody tell? Can anybody tell that these two terms I am actually
parameter is ideally statistics is ideally for sample, but parameter comes for the population.
Yes, yes. So parameters are for the population. Okay, let me just give you one example. Suppose our MNIT. Okay, so our MNIT in I'm trying to study that what is the ratio of male and female percentage. Okay, or you can say the male and female percentage in the suppose final year students. Okay, yeah, a numerical value that describes a characteristic of entire population. Yeah, very good, very good. So let me just give that example. Right now, here what is happening? I am trying to find out that what is the male percentage and what is the female percentage. Okay, what is the male percentage and what is the female percentage in the students of final year. Okay, now the thing is that suppose it is having in the final year, it is having around 1200 students or 1500 students. Okay, and I don't have any kind of information with me that what is the percentage of that, percentage of male, percentage of female, right? Now what I'm trying to do, that I'm basically randomly selecting some of the branches, okay, departments. So many of them are 120 kind of strengths, right? So I'm actually collecting data from that, and I'm basically trying to find out that what is the basically I have taken suppose 50 or 60 students, okay, randomly selected from different departments, and I have basically calculated how many males are there, how many females are there. Now what did I do? I basically created a sample from the population. I have created a sample from the population, and this sample is basically based on that I am finding out the male percentage and female percentage. That is known as statistics. Okay, that is known as statistics. So statistics are the characteristics, numerical characteristics or descriptive or visual characteristics of the sample. Okay, whereas the characteristics of the population, they are known as parameters, right? Now point estimate and interval estimate, let me just tell you what happens. That suppose I am trying to find out that what is the mean time, average time that is taken to reach airport from our campus. Okay, so sometimes it is suppose 30 minutes, sometimes it is suppose 15 minutes, sometimes it is suppose 20 minutes. Okay, in this way basically I'm finding out. Now as I'm telling that I'm interested in average of the time taken by if I'm traveling from MNIT to the airport. Okay, so I can just mean them. Okay, I can I can try to find out what is the mean time that is taken. Now is it actually good for us? If anybody asks you that what is the time that is taken on an average from this MNIT to airport, then it will be always better to give that, okay, it will be between suppose 15 and 20 minutes. It is always better to give a kind of interval rather than a point value. Okay, so here from here actually you can understand that what is the basically difference between point estimates and interval estimates. Point estimates are talking about only a particular point value. Okay, it is talking about a particular point value, whereas around that particular value, if I bring my confidence level, okay, that I am confident, that 95% confident that it is between 15 to 25 minutes, okay, then basically I can create, this is basically the interval estimate, which is showing 95% confidence of mine, okay, in gauging the distance between the MNIT campus and the airport. So could you understand this one? So interval estimates are always better than point estimates. Okay, but the thing is that these interval estimates are derived from these point estimates using in this particular frequency approach, because there are many things you actually you have to set. Okay, there are many free parameters. That what is your confidence level? Are you 95% confidence? Are you 98% confident? So in this way, basically we do. Achha, what is this confidence level? Confidence level means that you are doing a particular experiment, suppose for 100 times, and in how many times you are expecting to be successful in your experiment. Okay, that is known as confidence, and level of significance is just 1 minus that level of confidence. Okay, these are very basic things which you should know. Okay, it doesn't matter because we are not going into that much into those things, because here the whole basically idea of this predictive analytics will be a little bit different from this particular frequentist approach. Okay, so this is where I'm basically, let me now go into directly into this particular random variables. So random variables, I told that variables which are having an uncertainty associated with its value of occurrence. Okay, so it can be suppose the head or tail coming in a particular coin tossing. It can be suppose what is the probability that number of heads will be more than number of tails. Okay, in this particular set of coin tossing, this kind of several random variables can be possible. So random variables, basically I'll be denoting it using RV. Okay, so we actually use uppercase letter for this random variable, and whenever it takes a particular value, okay, so that is known as realization of that random variable, realization of X, that we denote as small case. Okay, so random variable is denoted by uppercase, realization of X is denoted by small case. Okay, This is the notation we'll be using. Now the thing is that what are the properties we actually we have already seen in this earlier lecture, as well as many of you already know that whenever it is basically the random variable, not a simple variable, so mean becomes expectation. Okay, mean becomes expectation, right? So mean generally we that is a kind of frequentist terminology. Yeah, please. Yeah, so mean is actually a frequentist kind of terminology. Okay, generally we write it as summation of xi by n. Now, if you are basically delving it more into this, then we can actually write that it is 1 by n summation of xi, right? And we can write it as 1 by n summation of, or we can actually expand it like x1, x2, dot, 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 xn, n observations, right? So now I can actually write it as 1 by n x1 plus 1 by n x2 plus dot, dot, dot plus 1 by n xn, right? Now, why I'm writing it in this way? I'm telling that each of the observation or realization of this random variable x, they are having the ratio of occurrence, or you can say chance of occurrence, as 1 by n. Okay, are you getting my point? So here I'm telling that this 1 by n, okay, is associated with all, it is actually multiplied with all the observations, 1 by n, 1 by n, like this it is going. So what is this 1 by n? It is basically chance of occurrence, that out of n times x1 has appeared once, out of n times x2 has appeared once. Okay, like this we are telling. So we can actually extend this thing into our expectation. So in expectation, we generally write it as bold-faced this particular e of x. Okay, and e of x we can write it as summation of small x. Okay, and this one, right? In case of x is discrete. Okay, and if it is continuous, then we'll be replacing this particular summation using integration. Okay, so this will be f of x, okay, and dx. Okay, so this will be minus infinity to plus infinity. Here also we write it as minus infinity to plus infinity in case of summation. Okay, so these are very rudimentary things. I think many of you know, right? So here, what is happening? What is this fx equals to x? So this is basically called as PMF. Okay, probability mass function in case of discrete random variable, and in case of continuous random variable, we call it as PDF. That is probability density function. Now, this is one property of, or you can say one statistic of a particular random variable. Second statistic will be the variance. Okay, so variance, how do we write? We write it as this, as x minus e of x whole square f of x. Okay, in case of discrete, and in case of continuous, it will be x minus e of x, right, whole square, then fx, then dx. Now there are some identities, okay, we are going to cover right now. Okay, so what are these identities? That suppose I am having two random variables, so x and y. Okay, so two RVs, x and y. Okay, and we are interested in finding out this expected value of a multiplied by x plus b multiplied by y, where this a and b, they are constants. They are constants. Okay, and this is suppose plus minus. Okay, plus minus, it will be covering all the cases possible, right? Now this will be how I can expand this, because why I'm telling all these things right now, expectation, variance, and all these things, that this will be several times it will be used. Okay, after we enter into Bayesian analysis, several times we will be using this. Why expectation and variance only? Okay, expectation and variance are the most, you can say, popular you can say statistics, okay, popular statistics by which we can actually denote any, or we can describe any kind of probability distribution. Okay, that's why we are bringing in this particular expectation and variance in a descriptive way. Okay, so if I expand this, then can anybody tell that what will be the result of this? If I expand this,
A E of x plus B E of y.
okay, so A E of x, who told this? Saurav.
Yes, sir.
Okay, very good. So A E of x plus minus B E of y. Okay, so what is happening here? The constant, okay, the constant will be coming as it is outside the expectation, and expectation will be applicable, expectation variance and all these things, they will be applicable to the random variable. So here you have to basically find out that what is my constant and what is my, or you can say what is my parameter and what is my variable. Okay, so A and B are the parameters here. Okay, A and B are the parameters here. So we are basically not this. So whenever it is coming outside the means whenever it is inside the expectation or variance, I'll be seeing. So it will be coming as it is outside. Okay, so there will be some change in case of variance, but in case of expectation, it is like this. Okay, now if I tell you about variance of AX plus minus BY, then how it will be coming? Can anybody tell?
So it will
Saurabh?
be A of square of x and then followed by B of y.
Plus b square v of y plus minus
Minus
2
plus minus of 2 times of E of x
ab
into E
cof x and
covariance
y.
of
Okay, so
y.
what is this cof? Cof is basically covariance, right? So whenever I am calculating this variance, this covariance will be coming into picture. Now, if these two random variables are independent of each other, then this cof can be 0, right? Now the thing is that suppose a little bit more about this particular variance. So anybody is asking anything? Tell me. Okay. So V of X, if I tell you. Okay, so V of X is actually written in terms of expectation. Okay, so expectation, if I write it in terms of expectation, then it will be E of X minus EX. Okay, whole square. Okay, that is variance of X. Okay, so here you can see, it is basically so in probabilistic machine learning and deep learning, you should be little bit aware of reading the statements, that what exactly it is trying to say. No need to, means you are basically, you should recognize the expressions. Yes, please tell me.
Sorry to interrupt you, sir, but I believe variance of x is E of x whole square minus of mu well E of x square.
Sorry, come again.
So what I'm trying to say is
Variance is,
variance of
yeah,
x
so we
E
write it as this
expectation of
one.
x square.
Yeah, I'm
Yeah,
coming to that.
and
I'm coming to
then
that. I'm coming to that. So how we are coming to that particular expression, I am just telling you how we are coming to that expression. That is a derived form of this one. Okay, so basically inside the bracket, inside the square, I have to expand it. Okay, so it will be E of x square, right, minus 2 into x into E of x, right, plus E of x whole square, right? Is it okay? Is it okay?
yes, sir.
So now, if I am taking out the terms, if I can basically operate the expectation on these different terms inside, okay, then what I'll be finding that it will be E of x square first, right? Then minus 2 is a constant, so 2 will be coming outside as it is. So 2 of expectation of x multiplied by ex, okay? Then E of x square, right? Now what will happen, that it will be E of x square minus this 2 has come outside already. Now expectation is on x multiplied by ex. So here what is the variable and what is the parameter, what is the constant, what is the variable and what is constant? for the
So
second term.
variable is x and e of
Variable
x
is
is
x. E of x is constant. So
constant.
it will be 2e of x, okay, multiplied by another e of x, okay. And the last one, okay, the last one, e of x is a constant one. E of x is constant one, so its square is also constant. So e of x square, x whole square will be coming as it is, right? Now, if you can do the algebraic manipulation, then you will be finding that it is coming as e of x square minus e of x whole square. So isn't it the same expression what you were telling, sort of?
Exactly, sir. Yeah.
So this is actually coming from this derivation. Why I'm telling about this particular derivation? Because lots of this kind of derivations will be coming. Okay, they are on the way. So you have to be in a situation, or you have to be in a position to recognize that what is happening. I'm not telling that overnight you will be becoming a statistician. Even I am not also a statistician. I am engineer. Okay, I don't have any formal degree in statistics. But the thing is that how could I develop interest in statistics? These kind of derivations. These derivations, this might look Greek or Hebrew to you at the very first glance, okay, but the thing is that if you spend little time in understanding that exactly what is happening, okay, then you'll be finding that this is very interesting. These are the expressions which are ready-made kind of given to ready-made kind of given in any statistics books. Okay, they generally don't explain it in the this kind of descriptive way. The illustration basically you have to do, okay, or you have to do this homework to find out that how these particular expressions are coming. Okay, so this is what actually I was trying to do. Achha, now PDF and PMF, so for the random variables, so PMF, okay, it is basically denoted by f of x. In both of the cases, basically it is denoted like this. Okay, PDF or PMF, may it be x is continuous or discrete. Okay, so we generally write like this, that f is the function. Okay, subscript will be the random variable, and inside bracket that is the realization of that particular random variable. Always you try to read it in this way, that capital X or uppercase X is the RV, okay, and small case x is the realization. For realization. Okay, so I'm not writing it. I'll not be able to write it here. Okay, so PMF is for discrete random variable, and PDF is for continuous random variable. Now, continuous RV, right? This is discrete RV. Now the thing is that they are having some properties. What are the properties? That all these fx at some value x must be greater than equals to 0. They are coming from the axioms of probability. Okay, that probability must be greater than equals to 0 and less than equals to 1. Any kind of probability mission. Second is that in case of discrete one, that will be having this fx for all means from minus infinity to plus infinity. Okay, x, okay, that will be equals to 1. Similarly, in case of this is for discrete one, okay, for continuous one, it will be fx, this thing, that will be greater than equals to 0, and in case of this it will be f of x, okay, that will be equals to 1. Now why I'm telling you this thing? Voice gone? Hello?
No, sir, it's audible.
Yeah, somebody sent a message that voice gone. Are you able to hear me? Please raise your hand. Umesh? So, okay, so I think problem at his side. Okay, no issues, okay. Ha, okay, thank you. So many messages are coming. Yeah, okay, thank you. Acha, now the thing is that expectation, I told about in the last slide, that expectation we are writing it as summation of x fx, right? Now, in case of discrete, okay, so let us just take the case of discrete only. Now, if I tell you that it is, I want to find out the expected value of a function of the random variable, then basically how to write it down, that will be gx fx. Okay, that will be gx fx. So you can actually find it out that how I actually derive the formula for variance. Okay, how did I derive the formula of variance? So variance of x is actually expected value of x minus e of x whole square, right? Now, so what is inside this expectation? So for what I am actually trying to find out this variance. So variance is basically expected value of value uh, value of the random variable minus the expected value square, right? So this is nothing but the gx, and that is why I am writing it as summation of, okay, x minus e of x whole square, then f of x small x. Getting my point? So this is, and this is applicable to the continuous case also. I'm taking this thing in case of discrete, okay, but it is same thing is applicable for continuous case also. So this is the gx. Okay, now it can be anything. Okay, it can be any kind of function you can have. Okay, so see, suppose if I tell you that what is the I am interested in finding out e of log x. Okay, e of log x means this log x is the gx here. Okay, e log x is the gx here, and it will be given as summation of log x multiplied by fx. Okay, in this way we have to find out. Okay, so if I tell you that the simple that tossing the die, okay, or throwing the die. Okay, so die basically it is the face value. If it is suppose 1, 2, 6, okay, then this is the face value. Okay, this is the face value. So what is the probability? Probability will be 1 by 6, 1 by 6, okay, 1 by 6. They are equally probable, so that's why 1 by 6 is coming. Now the thing is that what is the expected value? Okay, so expected value is summation of, okay, summation of x multiplied by f of x, this thing, right? So how to find it out? This will be 1 by 6. Okay, this will be 1 by 6 multiplied by 1 plus 2 plus dot dot dot. Okay, so what is this 1 by 6? 1 by 6 is nothing but this fx of x. Okay, so it will be up to 6, and this 1 to 6, if you do the sum, then it is 6 multiplied by 7 divided by 2, so 21. 21 divided by 6 will be the expected value of the face appearing. Okay, appearing of the face. Okay, so this expected value may be fraction in case, which might be sounding very unnatural in case of dice throwing. Okay, but it can happen. Okay, next is, suppose if I tell you that I am squaring the face values. Okay, so I want to find out, or squaring, I'm taking this cubic value. Okay, cubic face value. So e of x cube I want to find out. Then what we have to do, this x cube is the gx here. Okay, so what we are going to do, that we'll be doing x cube in a most lucid way possible. Okay, but don't change this PMF. Okay, this is not changed. Okay, the distribution is not changing. What is changing? The variable is changing actually. Getting my point? So in this way, it will be 1 by 6 multiplied by 1 cube plus 2 cube plus dot 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 plus 6 cube. If I am interested in, suppose, expected value of tan x, tan of log of x, suppose. Okay, then what we are doing? So don't change there will be no change in the PMF. There will be no change in the fx of x. Okay, remember this thing. There will be no change in the probability distribution. It will be change only change will be on the variable. Okay, so it will be kind of 1 by 6 multiplied by, okay, 1 by 6 multiplied by tan of log of 1 plus tan of log of 2 plus dot 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 plus tan of log of 6. Getting my point? 1 by 6 is not changing. So the phase value 1 can come with probability 1 by 6. It will be always fixed. Okay, no change in the probability distribution. Where is the change? Change is in the variable. Getting my point? Why I'm covering this thing in more detail? Because all this kind of expectation and variance computation will be coming several times. Okay, and it will be all based on this Bayesian theory. Okay, that's why. Is it okay? Any doubt till now? Any doubt till now? Any doubt till now? Can you please tell? If you are having any kind of doubt, please tell me. Acha, next is I am coming to something called as moments. So what are these moments? Moments are basically, it can be two types. One is called as a raw moment and another is called as central moment. Okay, so raw moments and central moments. So moments are basically, you can say, generic approach to find out statistics. Okay, that means mean, variance, and all these things. Okay, for random variable, for random variable. Okay, now moments, they are actually written in this way. Okay, I'm writing it in terms of integration. So let me just make you little comfortable with integration. Okay, so integration x minus mu, or don't bring in this mu right now. So x minus x0. Okay, so x0, right? Then to the power c, okay, and then f of x dx or d small x. Is it okay? Now just see here, what is the thing here? Here basically, what is this x naught? Okay, so x naught is, what is this x naught? X naught is, it can be 0 or it can be the mean. Okay, so if it is 0, then it is called as a raw moment, and if it is mean, then it will be called as central moment. So could I make you understand? This is the generic approach of writing down the statistics of the random variables. Acha, now C, what is the C? C is basically, it depends upon that what kind of moment you are actually finding out. So if I talk about expectation, okay, so expectation E of x, how I am writing? It is actually integration of x f of x dx. Okay, so what is the x naught value here? It is actually 0. And what is c value here? It is 1. Is it okay? Is it okay? Are you following me? Okay, now if I am telling you that if I am having x naught equals to 0 and c equals to 1, and what is the central moment, then what it will be? What will be the expected value? Central moment will be 0. So can you just give it a thought? Okay, so x naught equals to mean E of x, okay, and c equals to 1. Then what is the, okay, I'll be putting this in your quiz. Okay, then I think it will be, you'll be able to do it. Then what is the moment? Okay, what is the E of x? right? So this is one question, right? Now, next is if I look at variance. So variance is basically V of x, okay, and it is x minus e of x whole square, okay, and f of x dx, right? Now what is the x naught value here? So x naught is e of x, right? Now what is e of x? E of x is basically the center of the data, right? Expected value. So that's why this is a central moment. This is a central moment. And what is c value here? That is 2. Okay, so variance is central moment of order 2. We write it in this way, or we tell it in this way. Now suppose I'm interested in, suppose I'm not writing that what is it called. So let me just write out the expression, then we will be telling you. Okay, I'll be telling you. So x minus e of x whole cube f of x dx. So can anybody tell what is this particular expression?
Skewness.
Very good, Saurav. Again, very good, very good. So this is skewness. Okay, this is skewness. What is skewness? Skewness is symmetry nature of the data, that how much symmetric it is, right? How much symmetric it is. So if it is fully symmetric, then we'll be calling it as zero skewed. If it is suppose skewed, or if it is suppose elongated towards the positive side, then we'll be telling it positively skewed. And if it is suppose elongated, the tail is elongated on the negative side, we'll be calling it negatively skewed. And based upon this skewedness, there will be several types of distributions. We'll be coming to that. Okay, so this is skewness, right? Now here, what is x naught? X naught is e of x, and c equals to 3. Acha, now if I tell you that x minus e of x to the power 4, now Saurabh don't tell, okay, let others tell. Okay, so power is 4 and x naught is e of x. Then boy,
Kurtosis.
very good, very good. So who is this? Ankita. Very good, very good. So c equals to 4, right? So this is called as kurtosis. Now what is this kurtosis? Kurtosis is basically the pickedness of the data, that how much peak it is. Okay, now normal distribution, it is having zero skewness, and kurtosis equals to 3. So if it is more than 3 kurtosis, then we'll be calling it as a kind of spiked kind of distribution. Okay, and that is known as, can anybody tell what is that known? If it is kurtosis is more than 3, kurtosis if it is less than 3,
Platykurtic and mesokurtic.
it is mesokurtic. If it is
Mesokurtic.
spiked, then it is called as meso. And sorry, platykurtic
Yes, sir,
is
it's meso
basically,
only.
no, platykurtic is basically platy, where the platy name is coming from. Platy is basically coming
Plateau.
from platypus. Platypus is having flat foot. Okay, platypus is kind of animal which is having flat foot. So if the distribution of the data is kind of flat, yeah, greater than 3 is leptokurtic, and meso is basically zero kurtosis. Yeah, why it is called as meso? Why it is called as meso? Meso is basically, that is the mushy stage. Mushy stage means it is expected. Okay, so that's how basically this meso name comes here. Platy means it is a kind of flat. Okay, so that's why if the kurtosis is less than 3, then it is called as platykurtic. If the kurtosis is 0, then it is called as 0, near to 0, then it is called as meso. And if it is higher than 3, then, or greater than 3, then it is called as lepto. Okay, so this is what actually random variables and expectation variance and moments. Okay, now there is something called as moment generating function. I am not coming to that. Okay, that will not be coming here. Okay, now some popular PDFs. Okay, so what are the distributions basically we are going to see here? I'll not be covering that much here in this particular session, but the distributions we are going to see, first is known as binomial. I think in the last session it was already covered. Okay, so binomial. Then binomial is basically coming from a distribution that is known as Bernoulli. So binomial, it is having two parameters. Okay, N is the number of trials, and P is the probability of success or failure. Okay, as the case may be. Now, how Bernoulli is different from binomial? They are from the same category. Okay, but what is the difference? It is having one parameter. Okay, and the number of trials in this case, how much? What is the number of trials in this case? It is 1, and there will be P equals to probability of success or failure. Now, where this binomial and Bernoulli are applicable? When we are having when two possible outcomes. Okay, so where it is coming from? This is known as bi. Okay, bi means two, and nomos. Okay, nomos means terms. Okay, so basically, when we are having two possible outcomes, then actually this binomial or Bernoulli will be coming into picture. Okay, so for now, just keep this in mind. We'll be coming more into this. Okay, next is Poisson distribution. That was also covered. Where Poisson is applicable? Poisson is applicable that number of, you can say, number of occurrences. Okay, so whenever, so this binomial and Bernoulli, basically it is applicable for P is a finite quantity, and number of trials. So number of trials in case of binomial, that is also a finite quantity. Now, what is the PMF for this? PMF for binomial is NCX p to the power x 1 minus p to the power n minus x. Right. So number of trials. So this is P of capital X equals to small x is given like this. And what is the value of x can go up to? So from 0 to n. From 0 to n, right? And this is binomial distribution. This is binomial distribution. Okay. Now, P of x equals to small x will be p to the power x into 1 minus p to the power 1 minus x. That is known as Bernoulli distribution. Bernoulli distribution, right? Now, it is applicable for P and N, both are finite quantity. Now, suppose I am telling that P is very small, okay, like 0.001 or 0.005, okay, this one, right? It is towards 0, okay, and N is a very large number, suppose. Then N tends to infinity. Then what we'll be doing, we'll be actually multiplying this N into P and we'll be calling it as a lambda. And then this particular Poisson distribution comes into picture. Poisson distribution comes into picture. So it is actually coming from binomial distribution only, but when N is very large and P is tending to 0. Okay, so these are the things. Well, these are, I think, many of you know. I'm just recapitulating. Achha, what are the other PDFs? Bernoulli, binomial, beta, multinomial, Gaussian, gamma, distance function, this one. Okay. Achha, next is what is multinomial distribution? How many of you have heard of multinomial distribution and where it is used? Can anybody tell? Multinomial? Can anybody tell me what is multinomial distribution? Can anybody tell me? So multinomial distribution is basically when you are having more than two possible outcomes. Okay, if it is more than two possible outcomes. So its PDF is given as, okay, its PDF is given as here, it will be coming, it will be not coming like this. It will be basically, yeah, P I am writing as capital N C, this one. M1, X1, okay, X2, dot, 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 XK. Suppose K possible outcomes are there, and x1 to the power k1, okay, x2 to the power k2, okay, like this. If it is coming, where it will be applicable, it will be applicable for it is mainly applicable for in this kind of where we are actually categorizing the documents into different categories. Okay, so document characterization, you can say document classification or document clustering. Okay, there, because we are having multiple possible outcomes. Okay, more than two. So these are some kind of popular distributions will be coming. Achha, there are some more distribution that will be coming into picture. One is known as beta distribution. Second one is known as Dirichlet distribution. How many of you have heard of Dirichlet distribution and where it is used? Are you all audible? Yeah, Dirichlet. Okay. Okay. Anybody else? So these are okay. These are continuous distribution. These are continuous distributions, but they help us in inferring this particular discrete distributions. Okay, we'll be coming to that later. So let us just not go into more deeper into this particular thing. I'm not telling you that you have to remember all this probability density function, CDFs, and all these things. You just try to recognize. Okay, you just try to recognize by looking at the expression. Can you recognize that? Okay, this might be from this kind of. So there might be some kind of you can say mistake in calculating the power, calculating the values. Okay, but the thing is that can you identify the form? Okay, so can you identify the form? Here actually what is happening that in binomial distribution and beta distribution, okay, sorry, binomial and Bernoulli, that is basically quite similar. Why? Because p to the power x into 1 minus p to the power n minus x in one side for binomial. And if I remove this particular NCX, now NCX is basically called as the normalizing constant. We'll be coming to that later. So the other one is p to the power x. Yeah, yeah, it is a product of, yeah. I'm not going into detail into that right now. Achha, so now this one, so Bernoulli is basically, it is p to the power x multiplied by 1 minus p to the power 1 minus x. So if I replace this n by 1, okay, then actually I can find out that it is having approximately same form. Okay, so in Bayesian analysis, Bayesian modeling, you must be very you can say thoughtful about identifying that, or you must have very, you can say, the common sense, you can say, or you can say the kind of the power of recognizing the things. Okay, so you must identify that which group does it belong to. Okay, which group does it belong to? Okay, so you have to basically, you have to be expert in that. Okay, now the thing is that popular PDFs, I'm not going into this thing. Achha, now Gaussian distribution. So Gaussian distribution is always also known as normal distribution, and this Gaussian distribution is basically, you can say, it is at the center of all statistical modeling, all kind of statistical modeling, because of its properties. So this is also known as normal distribution. Okay, and it is for the random variable is a continuous one. Okay, and it is having domain as minus infinity to plus infinity. Okay, or we call it as support also. Now what is the PDF of this? As it is continuous distribution, so we'll be calling it as probability density function. So PDF is given as f of x inside x. So this will be coming as 1 by under root 2 pi sigma square exponential minus x minus mu divided by sigma whole square and half, and x is in minus infinity to plus infinity. Okay, x is in minus infinity to plus infinity. This is known as the PDF of the Gaussian distribution. I think many of you know, right? Now we'll be going into a little bit more detailing into this particular Gaussian distribution. That first of all, it is a two-parameter distribution. Okay, so it is actually two-parameter distribution. So this is two-parameter distribution. Generally, we'll be working with two parameter distributions only. So what are the parameters? That will be mu and sigma square. Mean is talking about the location, okay, or center, that is mean, and sigma square is telling about the variance. Variance is used for identifying what is the spread. Okay, and means how does the PDF look like? PDF actually look like a bell-shaped curve. Okay, it is looking like a bell-shaped curve. Okay, so this is on the x-axis it is the x, and at the center it is the mu, and the spread is identified by sigma square, that is variance. Right, now this is a very simple form. Right, now we are going to something called as we'll be looking at. So this is a kind of univariate case. Okay, so it is a kind of univariate case we'll be going into. So this is univariate PDF. That means what is univariate? Univariate is basically one variable at a time. Okay, so this is univariate. So univariate case, the PDF is looking like this. Now, if it is suppose multivariate case, okay, multivariate means I am having multiple variables working together. So that time it will be f of x. Here it will be instead of small x, I'll be writing it as capital X. Okay, and we'll be writing as the okay. So let us just talk in the terms of normal distribution. So how do we generally write it? We write it like curly n. Okay, x. Sorry, this one x, and then semicolon. Then parameters are mu and sigma square. Okay, and this is a PDF. Now, in case of this one, multivariate case, it will be normal distribution. This x is now a vector. Okay, it is no more a scalar quantity. Scalar means it is having only one element. Vector means it is having multiple elements simultaneously. So normal distribution of x colon mu, and mu is this is a vector here. So if it is suppose d cross 1, okay, this is also will be d cross 1, and instead of sigma square we'll be writing as a capital sigma. Okay, so this is the variance covariance matrix, and its order will be d multiplied by capital D. Okay, so what will be the PDF for this? It will be, we'll be writing it as 1 by 2 pi, as we are having d dimensions. So 2 pi, so here it is 2 pi square root of 2 pi. So here it will be d times multiplied and then square root. Okay, so this will be 2 pi d by 2 to the power d by 2. Achha, next is that I had taken sigma square. Okay, sigma square inside the square root. Okay, so here instead of that we'll be taking the determinant of this variance covariance matrix, okay, to the power half. Okay, to the power half. Okay, so the square root is now coming on the determinant of this particular variance covariance matrix. So sigma, let me write it here. So it is covariance variance covariance matrix. So variance covariance matrix. Right, and sigma, how does it look like? So it will be sigma 1 square. Then suppose if it is two dimensional, then it will be sigma 1 2 here, then sigma 2 1 here, and then sigma 2 square. Okay, so the diagonal elements are the variances and the off diagonal elements are the covariances. So in this way basically we denote. Now come to this particular multivariate situation. So exponential will be there, then minus half will be there, and then x minus mu whole square by sigma square. How do we actually write it? Okay, so x minus mu whole square, if I tell you, okay, so how does it actually come in terms of matrix or vector kind of representation? So whenever you are having square term and you want to extend it into multivariate case, okay, in terms of vector and matrix, then what will happen, that inner products will be giving you this square. Okay, so what is this inner product? So we can write it as x minus mu transpose multiplied by x minus mu. And this will be a scalar quantity. Okay, so inner product is always a scalar quantity. Why scalar quantity? Because I am talking about a function value. Okay, normal distributed x comma mu sigma, that is basically at a single scalar value. That is a probability it is coming, right? So x inside exponential, we have to do some matrix multiplication, matrix vector multiplication, so that we can get a scalar value. So we can write this as x minus mu transpose, then sigma. So here, in case of univariate case, it was sigma square in the denominator. So denominator means if you bring it to numerator, then it will be sigma to the power minus 2, right? So now sigma square I am replacing with the covariance matrix, variance covariance matrix. So this sigma matrix to the power minus 1 will be coming, then x minus mu. Is it okay? Has everybody understood this? Has everybody understood this?
So
Univariate.
from the variance covariance matrix, how did you derive x minus mu transpose to the power transpose x minus mu?
Okay. So basically, it is coming from like this. So I'm telling you that x square plus 2xy plus y square. Okay. So this is actually nothing but x plus y whole square, isn't it? Okay.
Yes, sir.
Now if I tell you that write it in terms of matrix or vectors, how will you write it? So this will be x y, that is a vector, that is a row vector, and if I take it as a column vector, okay, then how much if I multiply this matrix multiplication, so it will be x square, it will be x square plus xy. So how it is coming, just tell me.
So x square plus xy plus yx plus y square.
Yeah, so x square plus xy plus yx plus y square. Okay, so this is coming as x square plus 2xy plus y square. So what did we do? That square terms, if I take, okay, so that can be written as a transpose of a particular vector multiplied by the same vector. Okay, so if the vector is in a column form, so take the transpose, that means it will be row. So row multiplied by column, okay, will always give you a scalar quantity. And this is nothing but the dot product or inner product. Whereas if I tell you that I want a kind of matrix, so then what will happen, that column multiplied by row, if you do, okay, so instead of x minus mu transpose into x minus mu, I am suppose doing the other one, x minus mu multiplied by x minus mu transpose. Then what will happen, you'll be getting a matrix if the original vector is in a column form. Okay, so column multiplied by row, that will be a matrix, and this is called as outer product. Achha. Now another very interesting thing from this, that whenever you are calculating this inner product, you are actually calculating distance between two vectors. Later you will be understanding this. I'm not going to delve into this right now. So calculating distance is basically doing the inner product between two vectors. Okay, so this is giving you the distance between two vectors. Always, you just take any case. Okay, you'll be finding like this. Okay, so in this way, basically, we'll be coming to. Achha, now a little bit more on Gaussian distribution. So now based on this, now we are delving more into Gaussian distribution, because Gaussian distribution will be coming more into this particular thing. And why it is coming? Because this is the base distribution by which we can model the situations. Okay, we can model the situations. Okay, now suppose P of x, okay, it is governed by two parameters. Okay, that is, one is your mu, another is gamma minus 1. Okay, big gamma minus 1, right? So what is this one? This is basically if I'm telling you that this is following normal distribution, okay, with mu and gamma inverse. Now gamma inverse is actually sigma, capital sigma inverse. Okay, gamma inverse is actually gamma is sigma inverse. Sorry. Is it okay? So this is called as precision matrix. This is called as precision matrix. So precision matrix is basically, sometimes it is very helpful for us to reduce our computation. Okay, so that's why basically we are doing. Achha, now another random variable I am taking y, okay, which is actually ax plus b. Okay, and it is having, so this is what I'm doing here. This is actually a linear combination of the original random variable. So y is actually ax plus b. Okay, so this is linear combination of x. Yes, Saurabh, tell me.
Sir, you are saying that gamma inverse is equals to a covariance, a variance covariance matrix. So how is it defined? Like, is it like well established, or is it just an assumption?
No, not assumption. It is basically I am acha, okay. So assumption means that I am telling that sigma, if I am taking inverse, okay, then it is that I am setting it to something called as the big gamma matrix. Okay, the variance covariance matrix, many a times it will be easier for us to take inverse, okay, because that will reduce our computation and very natural kind of logic will be coming. Okay, that's why
So it's more
we
of a representation thing, not something
representation.
established. Okay.
No, it is a kind of representation. So precision is basically 1 by variance, or you can say reciprocal of variance is precision. Variance, what does it denote? It denotes how much spread it is, right? And if I take, you just think about natural kind of, you can say, what is the interpretation that if I take that, what is the reciprocal of a spread? Okay, what is the reciprocal of a spread? That means I am trying to tell you that how close it is towards the center, or how precise it is. Okay, how precise it is. So preciseness is basically reciprocal of the spread. Is it okay? Could I make it clear? Later you'll be understanding it much more in a much more better way, because many more things will be coming there. Achha, so this y is actually a linear combination of the original random variable x. Okay, so here this will be given, this will also be this normal distributed. Okay, so it will be, mean will be ax a mu plus b. Okay, so mean will be a mu plus b. So here what is happening, that okay, so if I tell you that e of y, if I tell you, so this is becoming e of ax plus b, right? Now a is a constant, so expectation will be acting on x only, and b is a constant, so it is coming outside as it is, right? Now what is e of x? E of x is mu and b. Okay, so this is the mean of the y. Now the variance, it will be written like, okay, the variance, it will be written like L inverse plus L inverse A gamma inverse A transpose. How it is coming? So V of y, okay, V of I is V of E of x, ax plus b minus a mu minus b. Okay, so in that way it is coming, isn't it? Now this is becoming v variance of a multiplied by x minus a multiplied by mu, right? So in this way. Now, if you expand this, okay, in terms of the precision matrix, you can actually find it. So here, this A, when it will be coming outside, this will be A square, right? A square. Now, how you can actually write that particular A square? That will be A transpose. In that way, we can write it. Okay, because this is a vector here. It is not a kind of scalar here. Okay, so in that way, basically, we can find out. So these are some identities you. I'm not telling that you must remember it every time. Try to understand that what is happening. Okay, try to understand what is happening there. Is it okay? Acha. Next is that this is y given x. Okay. Acha. Sorry, I have this is the marginal distribution. So marginal distribution was covered in the last class. Marginal distribution of y. Right. Now the thing is that sometimes we will be interested in finding out what is the x given y. Okay, what will be x given y? Means just now I am doing the inverse one. I was telling that I know x. Okay, y is a function of x, and we are trying to find out what will be the mean and variance of y, right? But now I am telling that I know y. Can I go back to x? Okay, can I go back to x? So I am basically, and I have to write it in terms of this linear combination. Okay, not in this particular form. This is the marginal distribution. This is the marginal one. Okay, this is also marginal, but here it is becoming
Excuse me,
conditional.
sir.
Sorry, yeah, please tell me.
So why do we have a mu minus b in this formula of v of y?
Here from this one, you just look at this expression. That expectation formula identity.
Yes, sir, not that v of y
V
variance.
V of
V of y.
V of y. So V of
Yes, sir,
y is basically what is y? It is actually ax plus b.
yes, sir.
Y is ax plus b. Now, what is the expectation of a? That also you have to find out. Acha, okay. I got it. What is the problem? I have written it wrong. It will be expected value of, not typing, writing mistake. Yeah. Yes. So now it is squared of this. Okay. Now is it okay? Now is it
Yes,
okay? Yeah.
yes, sir.
Okay. Okay. Thank you for pointing out. Okay. So now I was telling that I know the marginal distributions of x and y, and y is a function of x. Y is a function of x. So y is ax plus b. So that's why now I want to go back from y to x. Okay, so how I can actually write it? So this is having full derivations, but I am not going into this the derivations because it will take time to derive all these things. So this will be normal distributed. So basically, what is the you can say usefulness, or you can say the best thing with Gaussian distribution, that uh, joint distribution of two Gaussian distributed Gaussian distributed random variable will be Gaussian. Conditional will be Gaussian. Okay, all kind of possible, you can say linear combinations, that will also be Gaussian. So Gaussian, the derived distribution from Gaussians, they will be Gaussians. Okay, that is the best thing with Gaussian distribution or normal distribution. So that's why basically these kind of identities actually you need to exclude. Okay, so this will be uh, sigma multiplied by A transpose L, okay, y minus b plus gamma mu. Okay, you just write it down. No need of delving into this right now. So this is the mean part. Okay, this is the mean part of x given y. Okay, and the variance will be coming as same as sigma or gamma inverse. Okay, you can just derive it, but I am not going into deriving it right now. And what is the sigma here? Sigma will be gamma plus A transpose L A inverse. Okay, and this is the a new sigma. It is not the original sigma. Okay, so I am not talking about this. I'm not using this particular sigma here, right? So this sigma I'm not using. I'm actually talking about the precision matrix. So this sigma is not the variance covariance matrix of X. Okay, remember this thing. I have just used this notation just to describe that how this precision and variance matrix they are related. Okay, so this sigma is gamma plus A transpose L A whole inverse. All these things will be coming in Bayesian linear regression and all these things. Okay, and beauty of this Bayesian is we can actually find out P of y given x or P of x given y. Anything actually we can find out. So this is the beautifulness of this particular Gaussian Bayesian thing. So what I am telling about is that suppose if you go for P of x given y. So by the Bayes theorem, we can write P of y given x. So this was covered already. So I'm just taking cue from that. So P of y given x multiplied by P of x divided by P of what it will be? It will be P of y. Okay, it will be P of y. So P of y given x multiplied by P of x divided by P of y. Now what is this first term? First term is known as likelihood. Second term is known as prior. Third, this term is known as marginal likelihood. Why it is called as marginal likelihood? What do you understand by marginal, by the way? Marginal means that I am removing the effect of other variables which are occurring with the query variable. Query variable here is y. Now it is associated with x. I am basically eliminating the effects of x to find out this. So this is marginal likelihood. We can write it as P of y given x multiplied by P of x divided by P of integration. In terms of integration, I'm writing. So this is P of x dx. Okay. So this is the margin. So marginalization is basically I am removing the effect of the other variable associated with the query variable. Here the query variable is y, right? Along with y, x is associated, means x is also coming. So I am trying to remove this effect of x from this, right? Achha, there are some other things which is basically known as partitioning this vector of random variables. Okay, I'm not coming to that right now because, but let me just write it down. Okay, so that you can actually follow it later. We'll be following it later. So suppose this x, that random variable vector, I am having two partition. Okay, so one is xa and another is xb. Okay, suppose in xa two elements are there and in xb three elements are there. Okay, so x is actually 5 cross 1. Suppose 5 cross 1. This is 2 cross 1 and this is 3 cross 1, right? Now as it is a multivariate case, so the mean vector that will also be 5 cross 1. Okay, and it will be written as mu a and mu b. So I am partitioning the random variable vector into two part. Okay, two part participation.
Not that
Partition.
difficult.
Sorry. Okay.
Okay.
The
Then,
covariance.
not that. I wanted to tell you.
The covariance matrix is given as, okay, so this will be sigma AA, sigma AB, sigma BA, sigma BB. Now, can anybody tell? So this will be 5 cross 5. Okay, why 5 cross 5? Because x is 5 cross 1. So covariance matrix will be 5 cross 5. Now, can anybody tell me what will be the order of sigma AA? What will be the order of sigma AB? What will be the order of sigma BA? And what will be the order of sigma BB? Can anybody tell? Can anybody tell?
Sir, A will be 2 cross 2
Very good. Then
and AB will be the maximum dimension, so it will be 3 cross 3.
no, AB. How? Then it will not be matching. See, this is 2 cross 2 means 2 rows and 2 columns, right?
Right.
So this must be 2 rows
and
and
3
total number of columns will be 5.
3.
So this will be 2 cross 3. Now
3 cross 2.
This will be 3 cross 2 and this will be 3
3
cross
cross 3.
3. Okay, very simple algebraic manipulation. Is it okay? Has everybody understood this one? Now we are now going into this, just like earlier, we are actually trying to find out, suppose P of XA given XB. Now we are understand. Now these things are getting a little bit complex. Okay, so how to find this out? This is telling me that partition A partition given B partition. So I have already told that joint probability, if the original probability distribution is Gaussian, then joint, conditional, all other means addition, multiplication, all will be basically, or linear combination will be all Gaussian. So this will be Gaussian distribution only. So I'll be writing it as equal to normal distributed, okay, with this XA, okay, and its mean will be mu A given B, and I'm just writing it, I'll be writing the expression for it later. So, and this will be sigma AA inverse, okay, sorry, gamma in AA inverse, big gamma. So this is in terms of precision matrix I'm writing. So what is this mu A given B? So this will be mu A minus gamma AA inverse, okay, then gamma AB, then XB minus mu B. So what we are doing here, the this is the marginal mean of A. This is the marginal, this is the precision matrix of A. This is the covariance matrix of A and B, okay, and this is XB minus mu B. Now you can just cross check that whether the order is coming as 2 by 2 or not. This will be coming as 2 by 2 cross 1. Okay, it will be 2 cross 1. Now see, gamma AA inverse is 2 cross 2. Gamma AB, okay, gamma AB is 2 cross 3, right? And then it is coming XB minus mu B, that is 3 cross 1. So this is basically 2 cross 1. This is 2 cross 2. This is 2 cross 3. And this is 3 cross 1. So finally it is coming as 2 cross 1. Is it okay? Understood this one? Okay. Now, if I want to have marginal distribution of XA, then it will be normal distributed, okay, and this will be marginal, this one, mu A and sigma AA, okay, in this way. So this is basically the partitioning of the distribution. Is it okay? This kind of partitioning will be used later, much later, but it will be coming. Once it will be coming, right? So, so get little habituated with all these kind of expressions, because these kind of expressions will be used in much larger way. Okay. Achha, next is that, what is the next topic? Next topic is transformation of distributions. Transformation of distributions, I will just write down the simple formula and will be coming to that later. Okay, because in the next session, Professor Sobi Chakraborty will be taking, so he will also be describing all these things little bit. So transformation of distribution, suppose I am telling that I am having, this is basically matching of the distributions. Okay, this is kind of matching of the distributions. So there can be several distributions. Okay, suppose I am taking normal distribution and I am taking, suppose, another continuous distribution, that is suppose gamma distribution, okay, which is skewed one. So one side it is suppose normal distribution, which is very much symmetric about the origin, okay, and another side it is suppose a kind of skewed distribution like this. And I want to have equivalence between these two distributions in terms of area. So probability is basically area under the curve. I think all of you know. Probability is area under the curve. All of you know. So suppose I want to find out the equivalence between a particular area which will be same in terms of area. Okay. So suppose this is a stripe. I'm having. This is the stripe I'm having. Okay, and it is having a very small length, suppose d of x, and this is suppose f of x. This is a normal distribution, and this is suppose f of y. Okay, and I know that y equals to g of x, right? So from this, can I find out, from this normal distribution, can I find out the same area under this particular curve? Okay, so here it might be kind of this much. Okay, why this much? Because here you can see the height is quite larger. Okay, in terms of the as compared to the length of this stripe. So here I'm telling it as this is a dy, and this is the height is basically this distribution density value. Okay, so what is happening here? This transformation of distribution, basically there are two identities, two properties. You can tell that integration of fx, this one is 1 minus infinity to plus infinity, and integration of fy, that is also 1. Okay, so minus infinity, that is also 1. So these are properties of probability density function that must be always met. Okay, without that it will not work. Okay, next is that I want to find out the equivalence between this area m1 and area m2. Okay, so here what I am going to do, that as we are considering that they are equal, so as m1 is equal to m2, so fx of x multiplied by d of x is actually equal to f of y and d of y. So this is the length and height. I'm multiplying. Okay, I'm assuming that it is a rectangle, and I'm just multiplying. So this side it is for x, this side it is for y. Now I know y equals to gx. Okay, so I can do something like this, that fx of x is actually f of y multiplied by dy dx, and that will be put under uh, absolute under modulus. Okay, why? Because fx must be greater than equals to 0, fy also must be greater than equals to 0. That must be. Okay, otherwise it will not be a density function. It will not be a density function. But the thing is that depending upon value of this dy dx, okay, it might be negative sometimes, it might be positive sometimes. So positive, negative, it might give you negative value. So that's why I'm putting it inside this particular. So this is the length ratio. Okay, so I'm putting it inside modulus, right? So now I'm putting it. Yeah, Saurabh, tell me.
So actually, it's a length, right? Dy dx is the
Yeah,
strip length. So now
but
the question is, but then why for normal distribution we are taking it in the form of mod?
yeah, so for normal distribution, why I'm taking it as?
In a form of modulus function, the dx
Yeah,
is
so
coming in
now
modulus.
dx, it can be on this side. So generally what happens that the standard normal distribution, it is basically kind of um,
0 and 1.
0 and 1, right? So
Yes.
below 0 it is negative value, and above 0 it is positive value. So just to
But sir,
avoid any kind of confusion of negative and positive, okay,
okay.
I'm just keeping it inside modulus.
Achha.
Okay.
So, but suppose, but
Yes.
suppose, in case of just normal distribution where it's symmetric about mean,
Yes.
in that scenario, then we won't be taking a modulus function.
No. Symmetric about mean, but that must be generally we work with the standard normal distribution, right? Standard normal distribution is centered at 0. Below 0 it is negative.
Yes,
Above 0 it
that
is
is
positive.
fine.
Yeah, that's why.
Okay, sir. Okay.
So this is just create to avoid confusion. Okay, means no confusion should come, because area cannot be negative. Okay, got my point? Area cannot be negative. Probability cannot be negative, right? But the thing is that the associated things, if they become negative, then it will be going in a very wrong. It will be giving a wrong direction. Actually, there is a story I'll tell you later, that there is a kind of changing the intervals, changing the boundary of the integration. Actually, make it in make it the area can be negative by mistake. Okay, so then actually you have to change the boundary. Okay, you have to interchange the boundary. Now the thing is, so this is becoming f of y, and this will be g of x, then dy, and this will be dy dx will be d of gx dx, right? So this is becoming f of x equals to f of y multiplied by mod of gx. Okay, as it is a derivative, so it can take negative value. So that's why basically we are creating no chance of coming as negative. Okay. Acha. For multivariate case, so this is for univariate. For multivariate case, it is basically okay. I'll be taking 10 to 15 minutes more. Okay, because I have to just introduce the idea of MLE and MAP. Okay, so please bear with me. So fx of x equals to fy of gx. Okay, and inside this, it will be determinant of this mode of del y del x, and this is nothing but the Jacobian. Okay, this is nothing but the Jacobian, determinant of the Jacobian. Okay, so if I am having multivariate scenario, if I take this derivatives, okay, then what will happen, that we call it as Jacobian. Instead of a single derivative, we call it as Jacobian. Okay, so this is what transformation of distribution. Later we'll be having this transformation distribution in a much larger way. Okay, and rules of probability, I think it was already covered in the last. Okay, so rules of probability. So total probability, actually it is kind of marginalization. Marginalization. So it is basically, I can call that P of B is actually summation of P of B intersection A and summing it over all A. Okay, it is actually coming from this array of values. Okay, so one side it is suppose A with A1, A2 like this, and this side it is suppose B1, B2, B3. Okay, this side it is B, right? So here what I am doing, that I want to find out, suppose I want to find out P of B1. Okay, I want to find out. So here inside these are the joint frequencies of probabilities will be given to you. So this is called as contingency table. We have already seen in the last class. So P of B1, actually we can write it as P of, we can write it as P of, we can write it as P of B1 A1 plus P of B2 B1 A2, right? So P of B1 is this particular, B1 is this particular column, right? Now joint frequencies or joint probabilities I am having. So B1 A1, B1 A2 I am having. So from this I have to find out B1. So I am marginalizing out A, effect of A, and finding out. So this is basically P of B 1 comma A, and A is A1 comma A2. In this way, basically this is the total probability, right? And there is product rule is also there. Product rule is basically, product rule, it is basically coming from this particular P of AB. Okay, we can write it as P of B given A multiplied by P of A divided by P of B. It can be written as P of A given B multiplied by P of B divided by P of A. That also can be possible, right? And from this rule, actually it is coming as P of B given A multiplied by P of A equals to sorry, I have written something wrong. Oh, sorry. I have written it wrong. So P of AB is actually P of A given B multiplied by P of B. Is it okay? Or I can write it like P of, yes, it is right. And another is P of A given B multiplied by P of, sorry, P of B given A multiplied by, this is B given A multiplied by P of A, right? Now, is it okay? Now, it is telling you joint probability is actually likelihood multiplied by prior, and this is likelihood multiplied by prior in that way. So now we can actually talk about this particular P of A given B is actually P of B given A multiplied by P of A divided by P of B, right? Now these are the two events I was actually talking about. Now, as we are into Bayesian analytics or Bayesian modeling, so we'll be having a data set with us. So this is D is the data set, and theta are the unknown parameters. Theta are the unknown parameters. And our aim is to find out what is the unknown parameter, distribution of unknown parameter given the data set. Okay. And we can write it as P of D given theta, that is, this is called as likelihood, multiplied by P of theta and divided by P of D. Right? Now you already know this particular likelihood prior and this marginal likelihood. So here we are telling that P theta is the prior information I am having before observing the data, right? And P of theta given D is basically the updated belief, okay, regarding theta when I have observed the data. P theta is without the data observed. P theta given D is after observing the data, right? So here, this is likelihood, this is likelihood, this is prior, and this is marginal likelihood. Okay, this is marginal likelihood. Now the thing is, this is P of D given theta, P of theta, and in the denominator it will be P of D given theta multiplied by P of theta D theta. In that way we can write. Okay, Achha. So this is the rules of probability. Now Bayes law is coming from that only, so I'm not going into that right now. Achha. Next is that maximum likelihood estimation and maximum a posteriori estimation. Okay, so how many of you actually know about these two? Can you raise your hands? Can you raise your hands, Saurabh? Okay, anybody else? Anybody else? So likelihood, actually we have already seen likelihood is nothing but P of the data given the parameter. Okay, so this is telling me that for this parameter set theta, what the generated data, yes, parameter values that maximize the likelihood function. Very good, very good. So, but how to define the likelihood? Likelihood is basically that I am having a data generating process, and I want to identify that what parameters are actually generating this particular, or what values of parameters are generating this particular data. Okay, so likelihood is basically how likely that these parameter set have generated this particular data. Okay, that is given by P of D given theta. Now I am just taking this particular coin tossing experiment. Okay, coin tossing experiment. Coin tossing experiment, and in coin tossing experiment, basically, suppose I have observed the head, tail, head, tail, tail, head like this. Okay, so I have tossed a coin for certain times like this. Okay, now what is the parameter for this experiment? So parameter theta for this experiment is the success probability, or you can say the probability of head or probability of tail. We want to find it out. Okay, our aim is to find out what is the probability of head or probability of tail. Now, if you can find out probability of head, then you can find out probability of tail, because there are two possible outcomes only. So one will be one minus the other. Okay? Now the thing is that this is the parameter. So our aim is to find out that P of theta. Okay. Sorry, I want to find out that what will be the base value of theta. Okay, so I'm calling it as theta star. So in case of MLE, it will be theta star is given as maximized. Yeah, uh, coin tossing, then probability is 0.5, 0.5, but if we get 7 times, yeah, coming to that. Now this, you just remember in the very first slide, I told that we can calculate the probability in three approaches, using three approaches. First is that we are considering that equally probable outcome. So 0.5, 0.5 is basically equal probable outcome, because as there are two outcomes, so it will be 0.5, 0.5, half and half. Okay, we are dividing 1 divided by 1 by 2. Okay, so that is the probability of head, probability of tail. But the thing is that in reality, is it really the case? Because if you take a coin, simple coin, if you take, okay, आपके अगर pocket में है, so you can take it and check it. So the head portion, head side is little bit more protruded, because some more metal is there, because some emblem is there, right? And on the, and that is much heavier as compared to the tail side. So there is always a chance that whenever you are tossing it, okay, always a chance that head will be coming at the bottom. Okay, means tail will be facing you. There will be always a chance. So this is biased. This is called as biasness in your experiment. Okay. Now this bias you cannot actually remove. It's not possible. So first approach is that consider that it is equally probable. Second approach is that find out the frequency, and then just find out that what is the proportion of head and what is the proportion of tail. Okay, in that way. Third one is called as Bayesian approach. So now we are in the second approach. Okay, now we are in the second approach. Basically, what is happening, that we are trying to find out this particular theta star, which will be the base value of theta given the likelihood of the data. And that is what this particular maximum likelihood estimation is telling. So max of P of B given theta E over all theta, that is basically will be giving you my base theta value, right? So that is, yeah. Now, as this is a coin tossing experiment, okay, as this is a coin tossing experiment, so base distribution for the likelihood will be a Bernoulli distribution. Okay, Bernoulli distribution. So it will be max of, acha. Now another thing is also there, that I have observed so many head tail kind of tossing I have done, and I have to assume that that they are all independent tosses. So these are independent tosses. So how actually means one toss is not actually influencing the other toss. So how to incorporate mathematically here? So this will be kind of given as summation maximum of product of I equals to 1 to n. Okay, and d, instead of d, I am writing it as x superscript I, means ith observation. So what are the observations here? First observation is head, second observation is tail, third observation is head, fourth is head, like this it is going. So xi given theta. Okay, now as this p of xi given theta is following Bernoulli distribution, so this is a Bernoulli distribution. Okay, so it will be given as theta to the power xi multiplied by 1 minus theta to the power 1 minus xi. Is it okay? Understood? Now it will be just now you just watch. Okay, so if you are not understanding, please watch it, and later we'll discuss. Because in the next session this will be described in a more detailed way. So theta xi multiplied by 1 minus theta 1 minus xi. Okay, in that way. Now whenever we are having this particular product, okay, of several terms, it is better to take log of that so that we can get this particular we can say summation value as compared to product value. Okay, so this particular thing I am writing as log of this thing. Sorry, p of d given theta is actually product of I equals to 1 to n theta to the power xi multiplied by 1 minus theta to the power 1 minus xi. Okay, now taking log of this, it will be taking as, I'm just writing it doing some step jump. Okay, so this is summation of xi log of theta plus summation of 1 minus xi log of 1 minus theta. Is it okay? Now this is I equals to 1 to n. This is also I equals to 1 to n. Now summation of xi, if I tell, so I can safely assume that it is the, if I take success probability as probability of head. Okay, so success as, suppose, probability of head, success as head. Okay, then this will be number of heads log of theta plus this will be minus this thing minus 1 minus head, that means it will be tail. So this will be nt, that is number of tails, multiplied by 1 minus log of 1 minus theta, and nh plus nt will be the total number of tosses. Okay, now what we are going to do, that as we are trying to find out that what is the maximum value, so go for derivation, the differentiation. So del of log p d given theta, del theta will be equals to nh by theta plus 1 nt by 1 minus theta. Okay, and we'll be equating it to 0, and we'll be finding it as theta equals to, so this is the base value of theta, will be coming as nh by nh plus nt after some algebraic manipulation. Okay, after some manipulation, so this is becoming nh by n. Is it okay? Now you must be thinking, Arey, we already knew this. So proportion of head is nothing but number of heads have come divided by the number of tosses. Okay, but the thing is that in many cases you might be having several kind of situations. It will be very difficult for you to actually identify in this way. So coin tossing experiment I have taken to set the stage. Okay, to set the stage, right? Now, how this particular MAP, that is maximum a posteriori, is actually different from MLE. So MLE is nothing but MAP. It is basically a common sense approach. Common sense. Okay, so no prior knowledge is required. Okay, no prior knowledge is required. Right, now I'm going into this MAP. Okay, that is maximum a posteriori. Now in case of maximum a posteriori, so as it is posterior thing is coming, so theta given d, okay, it will be coming here. So this will be proportional to p of d given theta multiplied by p of theta. So I need a prior information. Okay, so this will be described in more detail in the next session. The concept of prior modeling, that prior information, how you can actually model that. Okay, so there is a very popular concept that is known as conjugate prior or conjugacy. So that will be actually coming here. So p theta, that will be considered as beta distribution with parameters alpha and beta. It is having a normalization constant. Okay, so this will be gamma alpha, gamma beta divided by, sorry, gamma of alpha plus beta gamma of alpha plus beta divided by gamma alpha multiplied by gamma beta, and it will be theta to the power alpha minus 1 multiplied by theta to the power beta minus 1. It will be just 1 minute. 1 minus theta to the power, 1 minus theta to the power beta minus 1. Okay, and theta will be actually it can take from 0 to 1. Okay, it is a continuous parameter. Just 5 more minutes. I'm wrapping it up. Okay, so 0 and 1. Okay, it is a closed interval. Now basically what is happening here? So this is posterior. So this is posterior, and that posterior actually I have to maximize. So theta star will be arg max. Okay, so this will just in the last, this will be arg max. Okay, so arg max theta p of theta given d, okay, equals to arg max p of d given theta multiplied by p of theta. Okay, now so this will be p of d given theta we have already seen. So this will be coming as before that let us just take the log of this. Okay, take the log of this. So this will be coming as theta to the power alpha minus 1. So this will be arg max theta. Okay, and this will be theta to the power nh, okay, multiplied by 1 minus theta to the power n tail, right, from the last, and multiplied by this prior formula, that will be theta to the power alpha minus 1. I'm not considering this normalization constant, theta to the power alpha plus 1, alpha minus 1, and 1 minus theta to the power beta minus 1. Now if I multiply this, then it will be theta to the power nh plus alpha minus 1 and 1 minus theta to the power nt plus beta minus 1. And in the same way, in the last slide, if we do this, then we can find out this theta will be given as nh plus alpha minus 1 by nt plus nh plus alpha plus beta minus 2. Okay, now this is the MAP. This is the MAP. Okay, so we can actually find out. Now this alpha and beta, they are the pseudo counts. Okay, so alpha and beta, we can call them as pseudo counts for this case. Okay, now if I take alpha equals to 1 and beta equals to 1, okay, so that time what happens, that beta 1 1, okay, that is actually nothing but uniform distribution 0 1. Okay, uniform distribution 0 1. Uniform distribution 0 1 means it does not have any kind of effect on the calculation. So, and another thing is that when alpha equals to 1 and beta equals to 1, the map becomes MLE. How? Because alpha is 1 and beta is also 1. If you put here, then it is coming as nh by n, same as the MLE. Okay, so this is what actually I wanted to cover. So right now I am stopping it here. So any kind of doubt if you are having, I can come at 2:15 when the next session is starting, and we can actually talk about that little bit. Okay, predictive distribution I wanted to cover, but I'm not, the time is already over, 20 minutes over the regular time. So Professor Sobi Chakraborty will be taking the next 2 sessions. So I'll be telling him to cover that predictive distribution. Okay, so, and you'll be finding all these things in a much larger way. Okay, that derivations and all these things will be coming in a much detailed way. Okay, so this is what. Thank you. So any kind of doubt? I have taken a little longer time. Any kind of doubt? Are you people there or already started lunch? Anybody? Yeah, please. In terms of application, yeah. So map is basically you are telling that once your prior information is available. Okay. So suppose instead of this 1 1, okay, instead of this 1 1, suppose you are having 2 2 or 5 5. Okay, alpha and beta. Then what will happen? That it will be actually creating more, you can say, understanding of this particular finding out the best value of theta possible. So as you will be having more and more prior information, you can actually contribute to interpretation in much better way. This is what Bayesian statistics is telling. Okay, in MLE we don't have any kind of prior information, so it is just kind of common approach, okay, or common sense approach. Okay, but in case of MAP, it is basically you are having prior information and you are encoding that in mathematical form, and then basically you are including that to find out the posterior, and we are all trying to find out the posterior. Now after this, so MLE on one side, and in the between it will be MAP, and after that basically will be, so no much info or less info for prediction of and MAP need. Can you please explain what you are asking? Can you please come with your question, please? Amarendra, Amar or something. Yeah, can you please come with your question so that I can reply it? Amar Chauhan. Mr. Amar. Okay, so again I'm telling that MLE, data MLE for more data MAP applied. No, I'll tell that suppose I have done only one coin tossing. Okay, and it has come as head. So what is the probability of head? Can I call it as 1? And can I call it as probability of tail as 0? Can I call it? Scientifically, no. Why? Because there is always a chance that probability of head will be between 0 and 1, but it will be nearer to 0.5, nearer to 0.5. Okay, that should be. But the thing is that if I go by MLE approach and only one tossing has been done or two tossing has been done, and both, suppose both have come as head, okay, then what will you tell? That it is your head probability is 1 and tail probability is 0. Is it possible? No. Okay, scientifically it is not possible. So MAP is much more scientific than MLE because I am having my prior information that it cannot be 1 or 0 directly. Okay, it cannot be, right? It will be nearer to 0.5. We have to find out, but it cannot be so sure that head will never come or tail will never come. We cannot tell, right? So that's why MAP is much more scientific. That brings some prior information. Okay, bring some prior information. So I can tell that it is equally probable. I can tell it that, okay, head is having little bit more going to downside and tail is coming more. Okay, so I can consider it that tail probability is suppose 0.7. I can start with 0.7 and head probability is 0.3. I can start. Then I'll be doing the tossing. And then what will happen? That it will be updated. Getting my point? So MLE is much more scientific than MAP is much more scientific than MLE. MLE is common sense approach. Okay, or you can say that it is a frequentist approach. MAP is I'm having some kind of information along with me, means prior information before I observe the data, and after observing the data I am updating my belief. Okay, this is how basically it is considered. Is it okay? Is it okay? Is the map estimate always consistent? What do you understand by consistent? So if I increase the number of samples, then will it have the same kind of behavior or not? So that is actually coming under Bayesian asymptotics. Okay, Bayesian asymptotics. So Bayesian asymptotics is basically then you have to understand the frequentist asymptotics first, that the consistency proofs. Okay, consistency proofs we are not going to consider that here. Okay, we are just giving you the idea. We are actually will be more on implementational part, better say. Getting my point? That is core statistics area, that consistency proof. Okay, so consistency proof is very interesting, but the thing is that it is it is kind of, if I go on increasing the sample size, will the behavior of the estimator be same? Kind of. So it happens both in frequentist as well as Bayesian approach, but yes, we are not going to cover this. Prakash, please tell me. Prakash, you have raised your hand. So I am closing it here. If you are not having any question, I'll be sharing the slides with you. Okay. Is the concept of unbiased estimators, OLS, MLE be covered in the... No, we are not going to cover this concept of unbiased estimation. Unbiased estimator, basically, I should say that unbiasedness is a property of frequentist approach. Okay. In Bayesian, basically, it is always some kind of biasness is there. So we have to accept that. Right? We have to, now that bias should not be too high. OLS will be coming in a form little bit, because now we are going into this particular Bayesian approach where likelihood will be kind of OLS. From that only, it is a counterpart of OLS only. Okay, so it will also be coming. Yes, little bit.